Hello everyone, and today we are going to discuss the model-free prediction using evaluation. We'll go in this lecture over some definitions, then we're going to discuss the Monte Carlo approach, and then temporal difference approach, and then other variations. We're going to go over them quickly, but the main emphasis will be Monte Carlo and TD0. Okay, now the basically we have to make the distinction between model-based and model-free, as we stated in early lectures. But the bottom line is this, that based on the knowledge of the models, the algorithms can be classified as model-based or model-free. And what we mean by model is really the transition probability distribution and the reward function. Okay, in model based, those approaches work when the MPD is known, and we do some kind of algorithms that are as we have explained earlier for the evaluation and the policy optimization. But when the model is unknown, then we have to learn from experience by sampling the environment. So this is the difference here. Planning in the case of model-based, learning by experience, which is sampled from the environment. If we look at the reinforcement algorithms one more time, there are those model-based, and as we have seen in earlier lectures, we have done evaluation to predict the value of the state values and the action values. We can do optimization, okay, and this is in the model base. Similarly, in the model free reinforcement learning, we do have also evaluation and optimization methods. Evaluation to evaluate the policy, optimization to optimize the policy. So, and always, as we stated earlier in earlier lecture, the evaluation is for a specific policy. The evaluation, we have a policy and we evaluate it. We have in the evaluation two approaches, offline and online, and in the optimization we have on policy and off policy. So let's go over the model free here. As we have we established what the model based and model free. Let's talk about the on policy versus the off policy. And this is really the main thing, which is really differentiates the optimization techniques. It really depends when we learn about policy from experience sampled from the same policy, or from experience sampled by a behavioral policy mu. So if we are learning from the same policy, then this is on policy. If we are learning from behavior policy, which is different than the target policy, then it becomes an off policy. So let's see here if we have so more in-depth definition or discussion. The definition will be clear if we go through this example here between the on policy and the off policy. Suppose a person is learning how to ride a bike. This person is constantly making adjustments based on how the bike reacts to the environment. Okay, so this is the current policy. The person's learning comes from his own experiences. Okay, from his own experience riding the bike. So basically, the agent learn and improve the same policy. This person is learning from his own sampling of success moves or bad moves during the riding of a bike. While if we look at the off policy, a person A is learning to ride a bike, but he can also observe person B. This is data from different policy. This is the behavior policy. Person A might still ride a bike a bit wobbly at the first using a target policy, but he or she is also incorporating knowledge from person B to improve the overall writing, which is the behavioral policy of. So the B now is behavior. So person A ride is the target policy. Person B ride is the behavior policy. So now let's take a look at the definition. What's an on policy? Agent learn about policy pi by interacting with the environment, that's means sampling experiences, using the same policy pi. This is on policy. Whereas off policy, agent learns about one policy, which is the target pi, while following or observing a different policy, the different person who is riding the bike, by observing a different behavioral policy mu to gather experiences. So again, if you are improving, learning and improving from your own policy, then this is on policy. If you are observing a different policy to improve your own policy, that's an off policy. Okay, so that is the deal about the online policy and off policy, which comes into optimization of model-free reinforcement learning. An example of online policy is SARSA, and an example of off policy is Q learning and DQN. Okay, now let's talk about the evaluation here. Okay, we know that we are in the model-free reinforcement learning algorithm space. The evaluation, which is the topic of this lecture. We can have offline methods and online methods. Let's see what's the difference here. Okay, now okay, if I we have, when we talk about offline and online, we really mean or emphasize the way we are updating the state value. Okay, in an offline updates are accumulated with an episode applied in batch at the end of the episode. Okay, so basically I run the episode, then I apply the update on the state values. So this is offline because I don't apply them as long as I am in the episode. I have to complete the episode. I have to reach the terminal state before I do the updates. While the online updates are applied within the episode. So every time I take a step in the episode, I go to the state value and I update it. So this is typical in tempo. So the temporal difference (TD) learning uses the online updates, while Monte Carlo methods use the offline updates. Okay, all right. Okay, so model-free methods do not require model for the environment. These methods can learn from experience by sampling the environment and observing rewards and states. And this is very important. We do not need to know the model, and by the model we mean the probability, the transition probability, and the transition probability and the rewards, the reward function. Okay, we don't need to know it, all right? And in fact, this is the real environment. This is the real practical environment. And in model-based, those model-based reinforcement algorithm, the model-based approaches, to be honest, are limited in their application. But we studied them to prepare us to the model-free methods. Okay, so here we did the basics, but real life situations are almost most of them are model-free reinforcement learning approaches. So we don't know the model, and we have to learn from experience by sampling the environment, observing the rewards and the state transitions. Now, there are two types of free model methods, much like we have done in the model base. We do evaluation, optimization. Similarly, here in model free, we do evaluation and optimization. Okay, so in policy evaluation, we estimate the value function for the state value or the action value for a specific policy. We do that in this lecture in two methods, Monte Carlo and temporal difference. Temporal difference, and we also have optimization, okay, and examples of that SARS and Q learning, and we will discuss those in a later lecture. Okay, all right. We did all of that. We discussed all of that. Okay, now, so let's talk about model-free policy evaluation. The idea is simply to compute the state value using the update equation. Okay, so what's the update equation? This is the update equation. Here it is. Okay, so first what we do, we run a scenario. Okay, we complete an episode, right? Then we update the state value. So the state value, the new one, the updated one, equal or gets the old state value plus some learning factor here, okay, learning rate, times the error. Okay, let's explain every one of them. What is alpha here? Alpha is the learning rate. And alpha, typically a parameter we dial to maintain the old information versus updating to the new information. This is the learning factor. So for example, if your learning factor is minimal, you will learn minimal stuff. And you will update those states slowly. And if you're and alpha approaches 1, because the value of alpha is between 0 and 1, and if the learning rate approaches 1 or 1, you will always throw away your old experiences and in favor for the new one. And obviously, we don't want to do either. We want to balance this by appropriate value for the learning rate. So here in the equation, the new value of the state, we keep the old one, right, times an alpha rate of the error. What's this error? The error is the target minus the old value, the old state value. In fact, now I can rewrite this equation, right, okay, as the updated state value is the old state value plus the learning rate alpha target minus the old state value. I can rewrite this equation as such by playing with the terms. 1 minus alpha times the old state value plus alpha times the target. And typically the target is in the Monte Carlo will be the expected total returns. Okay, the expected total returns, and we'll see how we can approximate this. But notice here it is back to this alpha here. Notice how I'm balancing between keeping the old values of the state value, what I have learned already, and getting a new value from this target. Okay, so alpha preserve getting a new information versus keeping the old information. Okay, so we run an episode and then we update these equations. All right, we'll see in an example how we do that. So in the Monte Carlo method, Monte Carlo method, it is a model-free, no knowledge of the Markov decision process, transitions or reward. Monte Carlo can or learns from complete episodes. And this is very important, which means I have to start from a start state and complete in a terminal state. Okay, so it is considered offline, no bootstrapping. Okay, so here's the issue. You can only apply Monte Carlo to episodic MDPs. All right, all episodes must terminate. All episodes must terminate. So MCUs the simple possible data, which is state value equals mean return, and we'll see this in the next slide. Okay, so the goal is really to learn the state value from episodes under policy pi. So the state value under policy pi, that's what my goal is. We obviously in the model free, we are sampling all these states and reward states and reward from the environment. Recall that the return of the total discounted reward is this equation from previous lectures. And recall also that the state value function is the expected return. So basically the state value is the expected of this expected total return. So to approximate the expected mean return, Monte Carlo computes an empirical mean return. So we are trying now to do what now? We're trying to approximate this, all right? The state value. We approximate it with this approximated state value by running scenarios, and then we say that the total returns of certain state S divided by the number of the times state S is visited, S over N, this is the approximated value for the stated value. Okay, we call this mean return or average return, mean return or average return. Okay, as n approaches to infinity, then we hope that this mean return will approach the state value. Okay, now let's take an example here, and in this example I have this Markov decision process. We have discount equals 1, and you can see that this is the state S0 has an action that takes it to S1 with a reward of 1. Then S1 can go into different states, S2, S4, S6 with reward 1, 1, 1. S2 can go to S3 with a reward of 1, and S3 can transition to ST, which is the terminal state, with a reward of 3. And similarly, S1 can go to S4, S5, and those are the rewards, and or S1, S6, S5, ST, and the reward as such 1, 2, and 4. Okay, we ran 3 episodes in this Markov decision process, and these episodes are as follows: S0, S1, S2, S3, ST. Notice when we ran this episode, okay, we can for sure tell that S3 has accumulated of reward of 3, because once it goes to ST, it has accumulated this much reward. And S2 has accumulated rewards of 1 plus 3, that is equal to 4. Similarly, S1 has accumulated reward of 1 plus 1, that is 2, plus 3, that is 5. Okay, you can see this is the 5 right here. All right, and S0 in this episode, right, accumulated reward 1 plus 1 plus 1 plus 3, and that is 6, and we can see this is 6. And number of times we visited states in this episode, which is episode 1, for state 0 we visited it once, S1 we visited once, 2 once, and S3 we visited once, and S2 we visited once. Now let's run another scenario, episode 2. And episode 2 takes me from S0 to S1 to S4 to S5 to S6. And now similarly, I can say that S5 has a reward of 4. Okay, so you can see here S5 here, this the total rewards here. Okay, and S4 has a reward 1 plus 4, so this is 5, okay? And S1 has a reward of 1, 2, 4, that is 6, okay? So you can see it right here. And S0 has a reward of 7, 1, 1, 1, 4, and you can see it right here. Now, for episode 3, we go from S0 to S1 to S6 to S5 to S2 to the terminal state. Again, S5 has accumulated another additional reward of 4, which is this one here. And S6 has a reward of 2 plus 4, that is 6. And S1 has a reward of 1, 2, and 4, that is reward of 7. And S0 has accumulated of reward 1, 1, 2, and 4, that's a reward of 8. Right? Now, to compute the mean return, which what we have defined here, the mean return, we divide the total returns over the number of times a state is visited. From these episodes, 3 episodes, the total returns for S0 is 6 plus 7 plus 8, and that is equal to 21. Now, how many times we visited this state? 3. So the mean return Fs equals 21, the total returns, divided by number of visited, which is 7. Let's take a look at S1. S1 accumulated reward of 5 from episode 1, plus 6 from episode 2, plus 7 from episode 3, and add all these together, that's 18. And how many times we visited those through these episodes? 3 times. So the mean return Vs equals 18 over 3, that is 6. So now the mean return for S0 is 7, and the mean return for S1 is 6. And now we continue. Let's come to S2 here. What is the total rewards for? How many times we visited this state in the episode that we ran? Once. So the mean return Vs equals 4 over 1, which is equal 4. And you can continue to all of them, computing one by one this mean return Vs. Okay, Vs. And here is Vs, and this is the mean return for the terminal states. The mean return is 0. Now, what we can say here is that we can do the update incremental after each episode. Once we do the episode, we incrementally go update all the states. We run an episode. We don't have to wait for 3 episodes. We run an episode and we update the states. And in the previous examples, we ran 3 episodes and we computed the state, the mean return. But you can do this episode by episode in an incremental way. In this case, okay, the updated value of the state value, this is the updated, equals the old plus 1 over NST, number of times ST is visited, GT minus VST. All right, and now we can approximate this. We can replace this 1 over NST. Well, this is the counter for how many visited, by alpha, where alpha, okay, is the learning rate, and this becomes much cleaner equation. Okay, so now my equation looks like the new updated state value equals or gets the value of the old one plus learning rate GT. Okay, that's the that's the total discounted return minus the old value of the state value. Okay, and now I can reorder the terms, alpha times GT plus 1 minus alpha, the old VST. That goes to the new VST. These are the update equations for incremental for incremental Monte Carlo. Now, what is the deal about the target here, and how do I replace it? In general, we say that VS, the state value, the updated value, equal the old one plus alpha times the error. And we stated that the error equals the target minus the old VST. Now, and in the earlier slide, we have stated that this VST plus alpha times target minus the VST, which is old. Now, what is the target here? Well, if you are doing incremental Monte Carlo, it is the total discounted return, much like we have showed here. It is the total discount return. But if you are using full Monte Carlo updates after multiple episodes or a batch style, then you would approximate the target as the total returns over the number of a state is visited. And this is more powerful definition here, because this is more powerful not because it's accurate, because it belongs to the real world equation. In the real world, if I don't know how to solve for or I don't know the value of GT, I just run episodes and compute it this way. Okay. Now, once we have established how we compute the state value or estimate it using Monte Carlo, which requires a full episode, we shift gears to another method called temporal difference learning. As we stated in the introduction, this is an online policy. And an online policy means what? TD learns from incomplete episodes by bootstrapping. What is bootstrapping? Bootstrapping means updates are computing using existing estimates, meaning I don't need to complete an episode. I can use the existing values to update my or to compute my update equation. So recall this equation here, we used it in the Monte Carlo, right? So the TD update replaces the GT here, which we approximated by S over N, okay? Um, we will say that this is will be replaced by the reward when I leave the state plus discount the state value of the next state. All right, so this is, we will approximate it as such. So we go back to this equation and we write it. The updated value of this state equals the old value plus alpha, the learning rate, open bracket, and the next value. Okay, so I think I have a little typo here. Let's see if I can. I'm sorry. Oops, sorry. I can just do this on the fly here. This has to be, yeah, there you go. Okay, much better now. Okay, so now the updated value of the states equals to the old value plus learning rate times the reward. Okay, when I leave the state plus the discount times the next state. All right, minus the old state value. Okay, notice here this V is the updated. This is this one and this one are the old ones, right? And this one is the next state. Okay, so we have to differentiate between these two notations. So in this case, my target here is the reward when I leave the state plus discount times the next state, the value of the next state. And this is my error here. This is my error. Okay, this is here my error. Okay, okay, so again, my target, this is my target, and this is my error. So temporal difference, we will update this equation every time I take a step from a state to another state. I don't need to wait until the end of the episode. Okay? All right. Now, so let's take an example here, which is a random walk example. This is a very famous example. We have here states A, B, C, D, E, and there are and two terminal states left and right here. And in any state, agent can move in either directions. So if you are in B, you can go this way or this way, C this way or this way, D this way, except E, you can go to R, A, you can go to L. And the rewards are here 1, 0, 0, 0, 0, 0. So the only reward I have is when E goes to R. And the correct values, when we run our algorithms, we find that the correct state values for A 1 over 6, B 1 over 2 over 6, C 3 over 6, D 4 over 6, E 5 over 6. And this is, of course, we're not going to run algorithm for that. We want to try to run simulations. And you can see as when we run simulations by 10 simulations, 100 simulations, and the values are approaching the ideal or the optimum values or the correct values. In fact, when we run algorithms, this algorithm using Monte Carlo with discount of 1 and learning rate of 0.5, you can see how these values are changing for those state values. They are approaching 1 over 6 for A, 2 over 6 for B, 3 over 6 4 over 6, and 5 over 6 for E. Okay, and now when we run TD with the same assumptions, these are the TD values, but they are slower to catch up. They are slower to catch up. So now, once we take Monte Carlo and TD and we run them for 1,000 episodes, notice how the state value trying to approach 1 over 6, right? The state value here is trying to approach 1 over 6, and notice also as well B here approaching 2 over 6, C 3 over 6, D, and you will see that you will see that the performance of Monte Carlo is better, okay, because they are catching up quickly or saturating quicker to the, at least in this example, okay, mostly, but this is, for example, not an indication over overall performance of the two methods, but in this example, Monte Carlo is catching up to the saturated corrected values quicker for the state values. Okay, so what's the difference between Monte Carlo and temporal difference? Well, first, it is the very obvious one, offline versus online. In a Monte Carlo method, you have to complete a full episode before you go back and update the states that you visited, the state values of your states you visited. Monte Carlo, you can take one step and go update the state value. Now, of course, learning from complete and incomplete sequences in Monte Carlo, you can only learn from complete sequences, complete episodes. But TD can learn from steps within a sequence. Okay, you don't have to have full continuity and episodic. So Monte Carlo works only for episodic terminating environment. Okay, but by the definition, that's how they work. But TD works in continuing non-terminating environment because we can sample and update the state values. In terms of Monte Carlo, they have high variance and zero bias, or minimal bias, we should say. The variance comes from the fact because we have to run complete scenarios, and those scenarios, they kind of take all kind of paths. So they are diversified transitions between these states, and that contribute to the high variance here versus here versus the TD, which has low variance and some bias, and again, this is because of we don't run a complete scenario, we run steps, we update within steps, and those and we use existing values of the states. We don't use we don't run a complete scenario, then we update all the states. We use existing values that contribute to some bias, okay, and low variance, at least in the beginning of the learning. Okay, convergence, good convergence, more efficient, good convergence for Monte Carlo, more efficient. This might vary per problem, but this is on average. Initial value, TD is very sensitive to initial values. Okay, so these are the two comparison between these evaluation methods for model-free Markov decision process. Now, there are different flavors of TD, and these flavors, I'm not going to go deep into them, but I'm just going to let you know that what we have used is that what is referred to as TD0. Now you can basically we did not go further in the states, right? But if you expand more, as you expand more the discounted return equation, all right, then you get into so you sample. So you go from one state to the next, or you can sample one to then to next state, from this next state to that state after. Okay, until you continue. Observe that the ultimate sequence, when we reach infinity, or sort of, okay, we will move from TD0 method all the way to Monte Carlo, because Monte Carlo, what it does is it tells you that you have to go through the entire path. Okay, so this is in terms of the stepping. Okay, and they have an interesting interesting update equation with this GT lambda, because when you run through these states, you construct this GT equations according to this one, and they call this a lambda return, and this is forward view. And you can see how this is you are looking at the states as you transition to the next state. In fact, you can have a backward view if you want, and even talk about decaying trace of count number. And there is interesting stuff there. I'm not going to get into the math of this, but the two main approaches: the front view, the forward view, and the backward view for the lambda return, which is part of the TD lambda methods. With that, I'm gonna conclude my session. These are again with the comparisons of the lambda and the difference variation, and these are my a slide about the Monte Carlo algorithm. This is a slide about the TD0 algorithm, and they are famous. They are in the textbook of our course. So please read them. Try to implement them in programming. And with that, I come to the conclusion of my session. Thank you for your listening, and we will meet you in the next class when we talk about the model-based control or optimization method. Thank you for your listening.